Okay, now comes to the last chapter of the pattern in the chemical world. Okay, this time we are going to talk about the transition element. So where are the transition elements? They are between group 2 and group 3. Okay, between group 2 and group 3, and then they are within period 4 to period 7. So they are right in the center of the periodic table. So these elements, okay, we call that transition elements. They are transitioning from metal to non-metal. Okay, so this is transition elements. We also call that transition metals. Okay. So for this chapter, we're going to focus on the first transition series only, from scandium all the way to zinc. Okay, zinc will be our last transition metals that we're going to talk about in this series. So you can see it from here, from the table down here. Okay, the one that I want you to pay attention to is the electronic arrangement only. So you can find that, okay, all of them, because they are starting from period 4. So therefore you will find that they will have 4 occupied electron shells. Okay, occupied electron shell. So you can find that, okay, every one of them, they got 4 numbers right there. But one thing very interesting is, okay, you can find that the outermost shells, you can see that in the outermost shells, all of them are 1, 2, 1, 2, 1, 2. So the extra electron actually is adding into the third shell. If you still remember for K, it is 2, 8, 8. The extra electron we're putting on the fourth shell. We're not putting in a third one. Calcium, we do the same, 2, 8, 8, 2. Okay, so at that time, okay, the extra electrons we're putting in outermost shells. But from scandium to zinc, okay, during the transition elements, okay, we found that every electrons, okay, we are filling in the third shell. So these terms, we give a name for this. Okay, we call this one next inner shell. Okay, this term is very important. Next inner shell. Remember, this is called next inner shell. It is not called next innermost shell. Okay, you may mix up with the outermost shell. This one is next inner shell. Okay, 3 words for that. Okay, so what we are filling in, okay, the electrons are filling into the next inner shell. But because of this, okay, you will find that, okay, the electrons, okay, normally the outermost shells, okay, will be loose, okay, as delocalized electron. But for transition elements, they are specials. Okay, what they are having is they're having the electrons in the outermost shell and also the next inner shell. These 2 shells, okay, the electrons in it can be contributed to the sea of the delocalized electron. So you'll find that they not only have 2 electrons, okay, in the outermost shells contributes, but also they may have more than 2 electrons getting in it. That's why, okay, we'll find that normally the metallic bond is very strong. Okay, because some of them may be contribute 2, some of them may be contribute 3, and the others. Okay, so metallic bond is quite strong. But one thing, just want to draw your attention. Okay, does it mean that these 15 electrons can be contributed? No. Okay, the mechanism is not like that. Okay, but that is out sea, so too complicated to explain right here. But you can think of at least they will have 2 electrons, and some of them coming from the third shell will come out, maybe 2 of them, maybe 3 of them, or things like that. Okay, so we will have electrons coming from the outermost shell and also next inner shell. So these find that, okay, this made that, okay, with more electrons, okay, in the metallic bond, so therefore they will be very strong. And due to strong metallic bond, obviously the physical properties, okay, will follow. So they have high melting point, more energy required to overcome this metallic bond. Because the metallic bond is very strong, the particles are hold tighter, okay, so they will have high density. More delocalized electron will have high electrical energy, high thermal conductivity, and because of the strong metallic bond, they are not easily breaking down, so they will be more malleable and ductile. And also because of strong metallic bond, the strength, okay, the tensile strength of it will also be very high. Okay, so these are the reasons, okay, why it will be like having these kind of properties. Basically, because in this chapter, the key point is because the electrons in outermost shell and next inner shell can contribute to the sea of the delocalized electron. So this statement is very, very important. Okay. explain a lot of properties of transition elements. So because of that, okay, we'll find that transition elements can be used in many different places. For example, titanium, okay, they will be like very strong and malleable. Okay, while this one, okay, is an oven, okay, we'll use nickel, okay, because we have like high thermal conductivity, and also they have a high melting point, they won't melt easily, okay. And then we'll have like the copper wire. This one is so typical, so they have like high electrical conductivity, and also they are pour into wire, so therefore you find that they will have a high ductility as well. Okay, and then this one, okay, is vanadium. Okay, vanadium. You're not quite familiar with this one, right? So vanadium, okay, they are malleable, so they can make a different shape of that, okay, and also they are very hard, so they can be a screwdriver. So in class practice page 6, so two questions is quite common again in the public exam. So the first one, asking why transition metals usually high melting point, then the metal is group 1, 2. Just like we mentioned, okay, you have to say that, okay, because the electrons in both outermost shell and the next inner shell, okay, can contribute to the sea of delocalized electron. So therefore, the metallic bond is stronger, more energy required to overcome, so therefore they will have a higher melting point. Okay, so the keywords goes here. Okay, second one, okay, explain why transition metals across the same period have similar chemical properties. Okay, so this I have to recall to your memories. Okay, we did mention in Form 3, chemical properties depends on the number of outermost shell electrons. So if you're referring to the table, you'll find that all of them are 2, 1, 2, 1, 2. Okay, so they're either 1 electron in the outermost shell or 2 electron in the outermost shells. So you'll find that the outer electron arrangement are very similar. The outer electron arrangement, that means the outermost shell. The outer electron arrangement are similar. So therefore, you'll find that the chemical properties will also be very similar. Okay, so what you can say is, okay, because they have similar outer electron arrangement. Okay, similar outer electrons arrangement, or you can even mention, okay, because the outermost shells of the transition metals have either 1 or 2 electrons, they have similar outer electron arrangement. Okay, so therefore they have similar chemical properties. Okay, so to summarize this videos, okay, first of all, you have to know that the transition elements, we also call that transition metals, they occupy the central area between the group 2 and group 3, where they are ranging from period 4 to 7. Okay, second one, the most important part, okay, electrons in the outermost shell and also the next inner shell can be contributed to the sea of delocalized electrons, and they have a lot of delocalized electrons. They have very strong metallic bond, and they bring up to these physical properties: high melting point, density, electrical conductivity, thermal conductivity, malleable, ductile, and also high tensile strengths. Okay. Last exercise, we also mentioned about the chemical properties. We found that they have similar chemical properties because each of them, they have either 1 or 2 electrons, okay, in the outermost shells. The keywords goes to they have similar outer electron arrangement. So therefore, you'll find that they have similar chemical properties. In the coming 3 videos, okay, we are going to talk about the chemical properties of these transition elements. Okay, next, we're going to talk about the color of the ions. Okay, so that's all for this video. Bye bye.